Hello, my name is Zhong Wang. I'm a computational biologist working at the Lawrence Berkeley National Lab. Today, I'm going to present Axolotl, a scalable Apache Spark-based library for high-throughput genomics data analysis. I don't have to emphasize on the dramatic increase in the amount of genomic sequence data for this audience. When I plotted the growth of sequence data in NCBI's short-read archive in the last 25 years, its growth rate surpasses Moore's law. This data explosion presents us with unique challenges. Existing tools and systems that we rely on are becoming outdated. They struggle to keep up with the rapid expansion of data. Compounding this issue, developing scalable solutions require a steep learning curve in parallel programming, which presents a barrier to many researchers. While we do have scalable solutions for specific tasks, we lack comprehensive end-to-end solutions. It's this gap in our toolkit that we aim to address with Axolotl. Our answer to this big data challenge is Axolotl. This is a tool we've designed with bioinformaticians in mind. We were inspired by BioPython, a highly versatile and powerful tool for bioinformaticians. We wanted to recreate that versatility with Axolotl, but with a greater focus on scalability. We decided to leverage the power of Apache Spark, known for its efficient handling of large dataset through a data parallel programming paradigm. We also want to take advantage of Spark's rich existing library of functions. We believe this is the key to address our scalability challenges. Why do we need another library, given there are several similar efforts that are trying to fill the gap of big data genomics? ADAM, for instance, is one of the most prominent examples also focused on Spark. It has shown promising results as there are several projects based on ADAM with a diverse functionality to form an ecosystem. However, there are a couple of limitations of ADAM. First, ADAM uses Scala programming language, a language most bioinformaticians are not familiar with. Second, ADAM is built from low-level data structures, RDD, which does not take full advantage of high-level optimizations Spark provides at the data frame level. Maybe as a result of these limitations, many ADAM-related projects are not being actively updated. We hope Axolotl can overcome these limitations. Axolotl uses column-based data formats like Arrow and Parquet. Compared with traditional row-based formats, these formats provide significant performance benefits when working with big data, especially the N+1 problem. For example, these formats make it easy to add a new column to a large data frame with millions of rows. We have developed an I/O module to handle many common formats in genomics. We adopted a light integration strategy. On one hand, we leverage existing optimized PySpark SQL functions to have good performance. On the other hand, we added a few Java Scala user-defined functions, or UDFs, to provide genomics-specific functions. Of course, there's a large set of third-party tools. For those, we have used Spark Pipe to take advantage of these POSIX-compatible ones to expand Axolotl's functionality. Using Python and DataFrame make it easy to use the library. The library is also modularized for easy development, and it can run on both HPC and clouds. Next, I will show you a couple of use cases to demonstrate these features. Here, I show this big slice pipeline. This is a good case to test Axolotl. Sochia, who developed this pipeline, uses to mine metagenomic dataset to discover biosynthetic gene clusters. It has 5 major steps, each include different apps. Satria's first question was, can he build the entire pipeline in Spark? The answer is yes. This is the schematic representation of his BGC module in the Axolotl library, an end-to-end implementation of Big Slice. You can see he's using Axolotl to run existing programs, including anti-smash. Most of the data is column-based data frame format for its performance. Reading many small files is a headache for Big Slice in this part of the pipeline. But in Axolotl, it's a breeze. Even without any optimization, Satria was able to load 800,000 small files in a couple of hours. Column-based data format did not increase storage, as we can see here. In fact, Parquet files are compressed. We actually reduced the data size from 8.3 terabytes to 2.7 terabytes. We don't have to write any sophisticated parallel programs or worry about data or job management when dealing with millions of files. Just a few lines of code with Axolotl. See the example I show here. Here is another use case. This is not necessarily familiar to many people in this audience, but in clinical genomics, one of the challenges is to calculate one's disease risk given the result from populational genetic studies. This is called polygenic risk score calculation, showing this formula, where all the SNPs of an individual genome are matched against a list of affected alleles of the disease dosage, weighted by their odds ratio, beta, and then sum up. The current state-of-the-art tool can do a few genomes and a few diseases at a time. It's difficult to scale it up. So the question is, can we scale up to do millions of genomes by hundreds of thousands diseases? Results from this scale may give us better understanding how the score distributed. Again, our first task is to convert row-based data into column-based, in this case, VCF. Once we converted both the genotype VCF to a column-based sparse format, we call it VSF, we can easily calculate polygenic risk score by joining it with another data frame from the GWAS state, also in column-based sparse format. We used the genomes from the 1,000 Genome Project, phase 3, got 2,500 genomes, and also we got 12,000 diseases from the EBI's GWAS catalog to test this function module. My grad student, Harrison Hu, got it done in 90 minutes with only 30 nodes. Because this calculation appears to be scaled linearly to the number of genomes, it will take us about 3 weeks to calculate 1 million genomes. Since we have more nodes, so we can add more nodes without any changes to the program, to the job. As we add more nodes to the 1,000 genome dataset, we roughly cut the time by half when we double the size of the cluster. We should be able to cut the time to do a million genomes and get it done in hours instead of days. Our bigger problem now becomes, where do we find millions of genomes? We may run out of data. We did see quite a few challenges when we developed Axolotl. For example, converting legacy data formats to column-based formats requires special adapters. A lot of times we have to develop them. And this intrinsic data or computing imbalance can severely limit performance. Some PySpark functions are incomplete or inefficient. we may have to write more Scala Java-based UDFs. Setting up Spark on existing IT infrastructure may require significant effort in configuration and fine-tuning. And our current plan for Axolotl is to collaborate with industrial leaders to develop open standard for array-based genomic data formats and add more function modules such as visualization, statistic to make it more versatile. And we plan to release version 1.1 at the end of the summer. Thank you for listening to my story of Axolotl. I hope you like it. I want to say we desperately need more developers to help us further test and develop this library. Or you can complain about it. You can accuse Satria's BGC modules or Harrison's VS module. You may blame all the other wonderful people listed here instead, or our wonderful founders, the Joint Genome Institute, or collaborators, Databricks and MemWorld. If you want to do that, please feel free to shoot me an email. Harrison also has a poster in this conference, and you can find me there to complain in person. Thank you.